materials. I just give a few brief biography of Mickael Gratzel. He's from École Polytechnique of Lausanne, from the Laboratory of Photonic and Interfaces. He has discovered a new type of solar cell based on dye-sensitive mesoscopic oxide particles. He is the father of dye-sensitive solar cell. He has one of the 15 top researchers in the world, and he works in many fields such as photovoltaic, electrochromic devices, as well as lithium battery and bioelectronics. He has many awards from different kind of scientific society. He has also many honorary doctoris causa from different kind of university. He's member of European Academy of Science and a fellow of Royal Society of Chemistry, and also in Science Academy of China, and so on. I am very pleased to introduce you here, Professor Mickael Gratzel, to give this talk this morning.
Thank you. Good morning. It's a pleasure to be here, and I'd like to thank Jean-Christophe Lacroix for son invitation. See here? See him. So it's a pleasure to be back in Paris, and so this morning I will talk to you about the work we have been doing in the area of mesoscopic oxide electrodes. So we have three applications. One is the dye-sensitized solar cells, but we also have been working on lithium intercalation batteries and the photocatalytic water splitting. And so I will touch upon briefly on those three topics. So without further ado, actually I should mention to you this is a solar cell. It doesn't look like one, but this is one of the embodiments that is unique to the dye-sensitized systems. You can print films, the patterns. These are very nice realizations, artistic type, from Sony Corporation. Sony has 100 researchers and engineers now working on the production of those solar cells, which have beauty, and not only beauty, but they also produce electric power. You can see the fan is this beautiful girl, I should mention, the fan that turns, and this is another Japanese, what should I say, gadget. It's a tree. These leaves are also dye-sensitized solar cells, and the electric power is making those butterflies flap the wings. It's not the type of terawatt application we are aiming for, but it's a very nice demonstration of this unique principle. That the dye-sensitized solar cell is the only solar cell that uses molecules to generate charges from light, and hence it is the only solar cell that imitates the natural process that occurs in photosynthesis. And it's also the only solar cell that separates the light absorption charge carrier generation from transport of carriers. In all the other cells, these functions are assumed by one material like silicon, absorbing light, generating charges, separating charge. Here we have that separation of functions. So, of course, we know the problem, energy demand going up. We have global warming, oil peak. Let's not get depressed, but there is a lot of anxiety here, especially with the latest nuclear disaster in Fukushima. And so renewable sources have to be developed very rapidly. It is a planetary emergency. And so I'm in this field, and I hope my lecture can convince some of the scientists from this community to come in and join us. And so the challenge is to find these 14 or 15 terawatts. That's the extra power we need by year 2050. We are consuming 15, and we need another 15, but that will not come from oil. So there have to be renewable resources, and so, but cost is an issue. And so this cell is very simple. It's the first three-dimensional junction until the this publication, there was only flat junction cells. And so this goes against the intuition a physicist had, I should say. The physicists always are aiming for perfect interfaces, and a thing like that is a horror for physicists. He thinks that there only be recombination and carriers cannot be collected. But the amazing thing is that yes, we have a disordered structure. These are TiO2 nanoparticles here, about 20 to 30 nanometer in size. And the porous space is filled by an electrolyte or a hole conductor, organic or inorganic hole conductor. And so this makes a three-dimensional junction, and sensitizer is placed on this film by a self-assembly process. Just dip the film in the solution, and the sensitizer goes on. It has the attaching grooves that make it interact with the TiO2 surface. And so that is a self-limiting process. That's very nice. It would be very hard to get that monolayer of sensitizer on unless you had a self-limiting process. And here you see the one embodiment, this transparent embodiment of the cell, and the fan again turning. So this is the cross-section, the dye, these red dots, injecting electrons in the oxides, electron having to make it through many hundred particles. The electron has to cross many hundred particles. And the bad news is there is no electric field that assists in the charge separation. So the only thing you can hope for is that since the electron is moving in one phase and the positive charge in the porous space, we have the hole conductor, that you master the interface, and that's really critical. I give you some examples today. You master the interface to the extent that kinetic control is exerted on the back reaction. And so the key parameter is the recombination time of the electrons with the oxidized redox mediator or the hole in the hole conductor. That's one parameter, the lifetime or recombination time of the charge carriers. The other key parameters, what is the time of collecting those charge carriers? And so if the collection time is 100 times faster than the recombination time, you're okay. You collect all the charges. And so impedance spectroscopy has been and some time-resolved methods that have been recently developed, voltage decay methods or current decay methods, they have been very valuable to get to these two parameters. And so so this device is part of a more general scheme of what we call nanocrystalline junctions. And so these junctions, they do have a high surface area, and that helps you to collect the light, to harvest the solar light. If you had the dye on a flat surface, it wouldn't work at all. It would just not absorb enough light. But not only, we also have this nano dimension, there's a nano congress, which is in the same size or range, the size of these particles of the same order of magnitude, like the device screening length of the electrolyte in the pores. So each particle is screened properly, and that means we can use insulating particles. They're all insulating, they're not doped. And so we can use those insulating particles, inject and withdraw charges, because the charge is screened on each nanoparticle level. That's another critical advantage. If you had a bulk film that's flat, you would have to dope it, and in the sensitization there would be issues of quenching of the excited state by the electrons that are used to dope. So all sorts of interferences, optoelectronic interferences, if you have to dope the film, but we don't. We don't dope it. We just use insulating particles. They get doped by the electron injection from the dye, and we can screen those charges by the electrolyte. We can also use a transmission line description of the diffusion and recombination charge carriers in these. I'll get to that later, where the key parameters are the transport resistance and the recombination resistance, and they both couple to what is called the chemical capacitance. I won't go into details. Juan Biscot has been one of the pioneers, our Spanish colleague, developed all of this. But let me tell you, the ratio of transport over recombination resistance is proportional or is equal to the ratio of these two time parameters, the transport and recombination time. So if we know the ratio of these two resistance, we know the ratio of these two time parameters, which I mentioned, be so crucial for the operation of that device. So the components then of the sensitized cells are the dye. Here we have one structure, which is the ruthenium complex. Very recently, the ruthenium complex have been beaten by organic dyes. So I saw it coming, but it has happened. I'll show you later which dye it is. And so we have the mesoscopic titanium film, and this is an ionic liquid. Industry likes to use ionic liquids as electrolytes because they have no vapor pressure and easy to work with, and you can solidify those ionic liquids by just putting nanoparticles, silicon nanoparticles, into the ionic liquid. So they're very, very important electrolytes. But we also have, as I said, this one embodiment which I just described to you, the dye coating these nanoparticles, and then the redox electrolyte, which has been mainly iodide, triiodide, but recently the cobalt complexes have emerged as a very viable and powerful competitor to iodide, triiodide. And so then we have also whole transporting cells. The cells, these cells that use polymers or organics or inorganic whole transporters, P-type semiconductors, they still are by the factor of 2. I mean, it's 7.2%. That's the conversion efficiency in standard condition. It's this device, and here we are now between 12 and 13%. So it still is a way to go. The reason why these don't work as well is recombination. We have a problem with carrier recombination in these systems. So just to show you, well, if I take an undoped anodized crystal, which we have made one of those actually, it cost us about 50,000 Swiss francs to make it. And because I had to pay somebody for a year to make it, nobody in the scientific community wanted to do that, so we finally did it. And so, but it doesn't, this is hopeless. It doesn't work because it's insulator. So we cannot use it as photoelectrode. You have to dope it and see what happens when you dope it. It turns black. And here's one of the problems, the interference of the black color comes from the conduction band electrons. It's the intraband excitation of conduction band electrons, and that produces quenching. So you don't have enough surface area, light isn't absorbed, you have the quenching. What comes out is a very poor device. The incident photon to current conversion efficiency is only 0.12%. That's, of course, nothing to brag with if you're going against technologies, the solid-state cells that have over 80%. But you can get over 80% when you use those nanocrystalline films. So here is the breakthrough in this technology was to go from the single crystal to the nanocrystals. And the nanocrystals are, of course, much cheaper. This film costs about 1 franc, Swiss franc. So maybe even less. And so, but scientifically, it was entirely justified to make those single crystals. We can cut them at different angles and see the faceting, how it affects the performance. So for fundamental research, this is a very important discovery. There are also others, I would say cousins now, that emerged that actually don't use electrolytes anymore. These are just nano dot sensitized films. And it's amazing that we can get up to 20 milliamps per centimeter. Here's something that I thought would never be possible. Actually, I went against my own convictions that this system could work, because here the lead sulfide does assume 2 roles. It does absorb the light, inject carriers, but it also is a whole conductor. So one should never be dogmatic. Here's a system that works because the carrier lifetimes are long in lead sulfide. Carriers are coupling very well through the particles because of the very low effective electron mass and hole mass. So here's an exception. It doesn't work that well, but 5% power conversion efficiency has been achieved. certainly promising to move along this path. So, but as a rule, we have that separation. We have a dye or a nanoparticle, a quantum dot absorbing light, injecting electrons and injecting a hole in the electrolyte. So that's different from the charge separation in p-n junctions. And so just to say that again in French, so you have the excitation and then the injection and regeneration of the dye. Now we have separated the charges across the interface. So positive charge is now with the hole conductor and the electron in the film, and that sets up a potential difference. Actually, this is fairly strong potential difference. It produces a stark effect on the absorption of the dye. But if you now connect the two sides, you get a photovoltaic cell that works as a regenerator for the electrochemical device. So the dye gets excited, ejects an electron, gets regenerated. 100 million cycles have to be sustained over 20 years. And I have written a paper in Compte Rendu some time ago where I went through those requirements. A simple branching ratio requirement. You have to have 10 to the 8 times faster injection than any bleeding channel from the excited state. And same thing here from the oxidized state of the dye. This can be checked. You don't have to wait 20 years every time. But very long-term experiments have been performed. The longest one, 4 years or 5 years, full artificial sunlight on the cell with very good stability for the sensitizer. So it's not all, but the sensitizers which are selected for these cells are selected such that they fulfill these kinetic requirements. And so now just to wrap up this initial part of my talk, we have collection efficiency is very important. I mentioned that to you. So very fast electron injection, then the regeneration. This is femtoseconds. This is nano to microsecond. Electron transport and interfacial recombination. And here we have these two time parameters, which are so important. So the case I have drawn here is the favorable one, where the transport is 100 times faster than recombination. If this is the case, the collection efficiency is over 99%. And so this was one of the points where we had discussion, and still a lot of discussions and debate going on. How come that we can collect from this disordered particle network, the carriers, without having electric field assistance? So it's by diffusion only. And so this is now shows the dye structure again. And we have here the picture where we just put the film in the dye solution and see how it turns dark. That means the self-assembly works. The film is now adsorbed. The dye is adsorbed the film through those carboxylate groups that coordinate with surface titanium ions. And that makes this very dark electrode, and that's the photoelectrode we're using for the dye-sensitized solar cell. Oops. So here's the injection. Excitation is shifting electron density from the ruthenium to the ligand, metal to ligand charge transfer. And then we have the injection in the 3D orbitals of the titanium, TiO2. Here we have kinetic trace. We see that femtosecond experiments, we see the rise of the oxidized dye signal. Last week I was in Valencia and somebody raised his hand and said, you don't have any femtosecond evidence, because I had to use a time scale of 1 microsecond here. So, but yeah, I couldn't understand the question, because you can see the rise is within, well, say 100 femtoseconds. And so the way things evolved was we started as just curiosity-driven fundamental research, the sensitization of colloidal particles, anatase particles. There was a first cell produced with these films that Jan Augustinsky had made in Geneva for as the high surface area films. Then we turned to the nanoparticles, and finally this technology has now scaled up its production. Products are being sold, and some of these products are shown here. but the real applications, large-scale applications will come from not only from these products, but from building integrated photovoltaics, because these cells can be made into transparent glass windows of different coloration that produce electric power from light. And so at the present stage, we have this situation. The power conversion efficiency is 12.2. This is a very important figure. You've got to have a good efficiency on the scaled-up version of the cell. It's not enough to measure tiny little devices of, say, 2 or 4 square millimeter, and then, well, I've got now 8%. This is not enough. You have to be able to scale it up, and not only that, you have to be able to produce the cell in an industrial process that has a yield of nearly 100%. And it has been one of the drawbacks of 6. 6 is hampered by the fact that the yield is low, 50%. And so this is very important. The 10% is an ICE-confirmed figure. It comes from Sony Corporation, the module. So it's not a figure that somebody has invented. Tandem cells are always higher. It's easier to get higher yields. The stability, I'm just going quickly, so this payback time. So these are favorable. Make the technology is competitive. It's not the best. It's unique in some ways. You can find niche applications where the others have no way to compete. But the technology is competitive with other thin film with a 10% module efficiency. It's no doubt. And so here's some just the Tata Daiso plant. This is in Europe. It's in Wales being built. We have the Fujikura has announced mass production. These are the dyes, the red and the black dye. And these cells are durable. They fulfill all the severance tests that a module has to undergo before you put it outside in the sun. This is the 85 humidity, stable at 8%, this module. So that's 1,000 hours, 85 degrees centigrade, 85 relative humidity. One sun irradiation, that's easy to meet. You don't have a problem on photodegradation. Heat cycle, that's more difficult. You have to go back and forth between minus 40 and 90, 200 times. So these tests are set by the international community, and if you pass it well, you can show your client, I have a cell that is stable and can be used outside. And so it's not surprisingly that these cells use these ionic liquids solidified with Si2 particles. These are the ionic liquids that Fujikura is using, but they're actually ionic solids. Once they are printed on, turn it a solid, but they work as well or even better than the liquids say. That's amazing. It's a jail, really, but it's amazing that this happens. And so I like to give you some taste of what the research is. I won't be able to, don't be afraid, I won't be able to go through all of this. I'll say a few words about the mesostructure. This is a nano conference, and some breakthrough in the sensitizers and redox mediators, and then I show some applications. And so the long-lasting discussion is whether or not the step from a random particle network to aligned nanorods or nanotubes, whether this gives you the advantage you think you have. The advantage you think you have is that now the diffusion will be one-dimensional, and you will perhaps get higher mobilities and less grain boundaries. Well, all these dreams have not been fulfilled until very recently. Last week in Valencia, Professor Snaith from Oxford, he says he has now tin oxide-based nanorods that do have the single crystal. So he has been able to grow those nanorods. And he says that he gets a very high mobility. So the collection time is shortened. Of course, that's good. That's good. So there are lots of structures, nanotubes, nanofibers. It's all very exciting. And I think we haven't played really fully these options. There's also these mesoporous worm-like structures that, and we are very excited about the macro, these balls. These are titanium balls that have about half a micron size, and you can see here. And actually, the invention was made in Australia by Graetzel, a professor at the University of Monash University, and also Yibing Cheng. So these two have invented this system, and we just applied it to make a cell that has a good power conversion efficiency. It shows you the advantage: beads over P25, get a better light response because the light is contained. When the light hits those particles, if it's within the absorption range, you have nearly 100% conversion of incident photon to electric current. So there is a surge of power coming out of these balls once you hit them with photons. And so that's good, but that's not the only advantage. You have light scattering, that multiple light scattering contains the light in the structure when you are in the tailing part of the spectral region where the sensitizer has a poor light absorption. So the various structures, the latest in the sensitizer is this ruthenium complex. See, this was our standard. I showed you the structure. The green curve is for the black dye. It's very similar structures. This was also a Lausanne invention. Then comes the Japanese colleagues from the University of Tokyo, and they have better response. They go up to 1,000 nanometers. This is amazing. There's one molecule. It's one sensitizer molecule that gets a very similar photon collection and conversion like silicon photovoltaic cell. It's a molecular silicon photovoltaic cell. Well, what is the structure? Well, di-X. So be my guest, but I have to tell you the structure is now known. I know the structure, I can't tell you. It still is confidential. It's a ruthenium complex. And so it's amazing you can get that optical response. And so the high IPCE values show that even with these panchromatic systems, you get good carrier collection. But we have been working along the donor bridge acceptor dyes, which are the next dye generation. You have a donor, pi bridge acceptor. Of course, there are many possibilities you can think of. Just think about how many donors you can. And initially we thought, well, let us be guided by our chemical intuition, but that was wrong. And so we made a few molecules that were terrible. They should have worked like this this tetrathiophylridine. Oh, wow, that's an excellent donor, so let's put this on. Well, things don't always work out the way you think, and so also the bridging part. So we need input from theoretical groups, and so we are now collaborating. The first paper with David Casanova and some of the codes that have been developed in the field of theoretical chemistry now, they're really good. They can predict the optical absorption of these dyes with the accuracy of 0.1 eV. So that's excellent. There's several methods now, and we have to use them, of course, very efficiently to guide us in the selection of these sensitizers. So one particular dye here comes out of Taiwan, Dr. Jiao and Yi. They made a D-pi-A dye with the porphyrin being now the bridging part, and this has given them remarkable efficiency with the iodide, triiodide, got over 11%. So that was for a while the highest efficiency that one could achieve with a non-ruthenium dye. The organic, that's a metal complex, but it doesn't have ruthenium in it. It's a zinc complex. And so you have the donor, we have the pi bridge, the acceptor. So if you do the calculations, Filippo De Angelis from Perugia did the calculations. You see the HOMO being now, it's not a pi-pi star transition in porphyrin. The HOMO is on the donor and the LUMO is on the acceptor, and they couple to the pi-pi star transition, and you get a very nice response. But then it turned out that if we use a new redox mediator, the cobalt couple, which gives higher voltages than the iodide, it's, this dye is here shown in blue is not, by far not as good as the one that has these alkoxy groups. It's coded YD20C8. Also C8, there's a C8 chain here, 2 C8 chains. So this, just read the subtle changes. There are subtle changes in the porphyrin structure which give a dramatic effect on the photovoltaic behavior. And why is that? Well, it's all the interface. I mentioned in the very beginning, the key to this successful operation of this cell is that you have to control the interfacial electron transfer dynamics. And so what happens with this dye is that apparently, when you draw the three-dimensional structures, you get a very efficient protection of the surface from the access of the redox mediator. So redox mediator can get to the Ti2 well, then it can back react. It still can regenerate the dye. It doesn't have to go to Ti2 surface. So that's why we get this 970 millivolts VOC, open circuit voltage. That's for us, it was a dream to get this high open circuit voltage. It comes along with a high current. Of course, if you don't have a high current, then the highest voltage doesn't help you because the efficiency is the voltage times current times fill factor. And so you can also see here the IPCE spectra much better for this alkylated or alkoxylated dye. And so then we have to push it to the maximum. So we made this dip here is costing you, it's producing a nice green color, but it's costing you photons. So we mixed another donor acceptor dye with this, which we actually comes out of, it's the first successful dye we made in our laboratory. It's coded Y123 after Chen Yi, my Chinese postdoc, that is very, very good in synthesis. And so, so we mix these two to get full spectral coverage. You see the black dots. Get very high conversion efficiency, over 80% across the visible until 720 nanometers. And that gave the record cells, which we are now over between 12 and 13. We have still little diffusion problems, but half a side, get over 30. So the photovoltaic potential of this system is very, very high. And so why is that giving a higher voltage? It's actually because we are losing with the iodide. We have a major loss in the regeneration. We lose by 0.6 volts. And of course, that is a cost. The VOC goes down. It's very hard in dye-sensitized solar cells that give good currents to more than 700-800 millivolts, which is always between 700 and 800 millivolts VOC. That's the voltage you get. But with the cobalt systems, we have been varying the redox potential. It turns out that 0.2 eV, 200 millielectron volts, is enough driving force to regenerate fully the dye. So actually, the loss can be reduced significantly. And we have been able to get up to 1.1 volt VOC, which is one of the highest of the photovoltaic cells. If I think about maybe gallium arsenide, even then, I think, I'm not so sure what the gallium arsenide may be close, but it's amazingly high potential. It comes with a high current. So we are really now, with this breakthrough, latest breakthrough, we have a good chance to hit the 15% bar, the DSC systems. So now let me move forward, just show you some applications. And I mentioned transparency, we have lightweight. This is these are very common parameters. I don't think I have to go through all of this. And so just focus on these nice colors. And here's some of the unique selling propositions we have. And so these are some German realizations. In Asia, a lot of people use these, make designs of motifs and to make it look, the cell look more beautiful. It's when the Asian culture, they really love beauty. See, this, I would never be able to make a solar cell look like this, but they can. Okay, so even in China, there's also a solar cell with a panda. This is printed with a black dye, so this part is photoactive here. The rest is not, but it's still turning the fan. So getting a lot of assistance and help from our Asian friends. Without the Asian research community, we would be really in a poor state, and so we are very grateful. And so this is the Sony solar chargers. These lamps also very beautiful, Hana, Akari, flower lamps. These collect light during the day, so these are autark. Put them in your room, you never have to put a cable to them. They will collect light during the day, and at night the LED gives it back to the battery storage system. So that's also a good idea. I was thinking about this sunglasses. So these are windows, more of the beautiful modules. This is now from the Fraunhofer. They have made very recently a press declaration. So they're getting now to 80 times 100 centimeter, 1 meter sized module. And Dr. Hinch has been working for years very persistently to get this meander kind of structure. It's very stable. It's all glass sealed, and it has been the biggest module that has, it's all screen printed. So very nice success. So we have, I showed you already this building integration. These are some street lamps, again, autark. Again, building integration. Here are the flexible cells. I don't know whether you know this person here. This is Christian Wolf. He's a German president on state visit to Switzerland last fall. And so he's seen here with Doris Leuter. Our president lasts only for 1 year in Switzerland, changes every year. so she was president last year. And they get along very nicely, you can see that. And especially since we made those nice presents here, the computer. We have the keyboard with the German colors and the Swiss flag. And they are powered by the Dyson-sized solar cells, the flexible ones. And so there are other applications, and I should mention the bag. And we have now, these bags are now distributed in India through a local manufacturing sites. The idea is to make the cells by the Indians in India. And so you see these, they love these bags, they carry them around all the time. And at night you can, even with a 1 watt lamp, you can get quite a lot of light out, a halogen lamp. So it doesn't consume any power. And so they should also mention the tsunami victims. This Toyota Aisin Seiki had launched production. These are also lamps that are powered by Dyson-sized system. A large number of these lamps has been distributed to the tsunami victims. And you see here how the Japanese are very well organized. So the packages arrive, and you see the lamp here, the LED lamp, and the very robust kind of the cells. And look at the happy faces of these two persons. They got their light source. We are all spoiled. We think we have always power, but what if the power lacks? Then you're really in trouble. And so, so this is now a race car that's also driven by Dyson-sized cells. Let me just look at my time. 5 more minutes. So we need storage, and so in this field we have used the nanocrystalline approach. Actually, Ivan Exner, a colleague who used to work for Swatch Corporation, and we had started this work on using nanocrystals for lithium-ion batteries. So let me just show you that. The first rocking chair battery was described in a paper which was published. It's totally ignored by our friends from the battery community. But finally, I got an invitation a couple of years ago, 15 years after that, that paper was published, I got an invitation to a battery conference. And so I presented that work. I said, look, can't ignore that we have been the first to propose nanocrystals. And of course now everybody, and we even applied for and got a US patent, but it's assigned to, it's a scientist's watch. so that's, the owner is watch. So the idea is that if you go to small size, you should cut down diffusion paths for lithium. So even if you have a low diffusion coefficient, 10⁻14, materials that are lousy as conductors for lithium, with a nano dimension, you gain this factor of R to the squared. So that's very, very important. And going from a micron to a nanometer buys you 1 million in intercalation time. So there have also been recently this manganese phosphate. This has resulted in HPL as a spin-off from our laboratory. It has recently been sold to Dow Chemicals. And so this material is now made in a ton quantity for these secondary batteries. Finally, I finished saying that storage also can be achieved in a way by producing fuels from light. That's something that's very much coming up again. It was a dry period over decades. Nobody was interested in this fuel generation. And now, going back to hydrogen or CO2 reduction, and so the idea is to have an N-type semiconductor. You can also use a P-type, but for oxygen generation would be the N-type. So the holes generate oxygen, and then electrons would have to turn around, and that's a dream, right? There's no one system that works efficiently, even though 30 years or 40 years of work have been done on these. But if you couple this in a tandem cell, then you're okay. You can provide the extra power. You need some extra power for the electrons. If this is a visible light absorbing semiconductor like iron oxide, we need some bias light. We need some bias potential to drive the hydrogen evolution, but that can be done by a Dyson-sized solar cell. There are many ways to do that in situ using a tandem concept. So we have been starting on iron oxide very low and miserable yields in '94. It was our first nanocrystalline iron oxide film. And things have dramatically improved by just working on the optoelectronic properties and the mesoscopic feature of these film. And so here's the APCVD with oxygen evolution catalyst, the cobalt catalyst. So this shows you we have been going through a death rally with this system, just trying to survive and showing advances, but it has happened. Persistency has paid off. And so the hematite is, of course, a very cheap material. It has a problem with short hole diffusion distance. These are all problems, but you can deal with those problems. And so in a single crystal, the very thin layer, the first nanometer work, because the whole diffusion length is a few nanometers. So if you have the optical absorption length is a few hundred nanometers, so you collect only from a few nanometers. It's not a good proposition. But with these cauliflower structures, we have the nano-sized features, and so you get to a point where you collect the carriers they produce within those cauliflower structures. And where we stand today, the latest about 4 milliamps. That's in a tandem cell. If that's a supported current, and would be about 6% efficient overall solar to hydrogen. And so we also use the cobalt phosphate, which has very nice IPCE. So we're still working on those catalysts. Iridium oxide is certainly the best, but it's also expensive. So cobalt is a nice alternative. And we had proposed it even before Gratzel, and we used cobalt ions on the surface iron oxide in 2006 and published it in JACS. So here's the electrode at work. See, this is rust, but rust can be made to work as a photocatalytic system. And you can see on the light the oxygen bubbles coming off. So this means the system is working. And the design we have is highly doped films, which the space charge layer that helps in separating the charges. So it's not entirely the same concept we use in Dyson's tight cell. So here's our laboratory. I finished. I noticed I'm getting within the 45 minutes approaching. The chairman is already looking at his watch. So this is our laboratory at Elecnano in Lausanne, and was taken in January. Unfortunately, we didn't have any snow, so very bad season for skiing this year. And so thanks to all the members of my group. We are running a big group. We have very motivated people, and we hope that the lecture I present here will encourage other young scientists or experienced scientists to join. And this is the funding. We are particularly grateful for the FP7 European Jewel projects, which have been generously supporting our work. So with that, I have finished. Thank you for your attention.
Thank you very much. We have just time to one or two questions or comments. No question? Okay, thank you again.